Are the citations for these guys on the web page as well?
Yeah, so
okay.
These books are listed on the web page and also on the list of projects. Everything is on there also.
Great.
So.
Federico, are any of those books like closer to what you're going to be doing than the others? Is there one or two authors that you'd recommend?
Not really. I mean, the thing is, there's this 3-volume encyclopedia of matrix. So this is one of them. It's called Matroid Applications. For example, what I'm going to be doing today is section 6 of Matroid Applications by White. But really, we're going to be doing different topics that come from different places, and so each time I'll tell you where it is. But there's not one book that I would really suggest over the others. And the one thing that I do ask you guys is that if one of you checks this book out of the library, you should tell everybody else about it. Maybe even put it on the forum. I have this book, so if you need it, let me know. The other thing I should tell you actually is that starting today, we are finally on the same day as the Colombian students. So we've had a delay of 1 day, but now we're on the same day, and so now the discussions on the forum will make more sense because we're learning things at the same time. So.
Does that mean what you lecture on now?
So they're going to learn what. Right. So we finish the lecture, and then an hour from the lecture, they learn the same thing. So.
I thought you couldn't transmit the lectures that fast. Or is that been fixed?
Now we can apparently.
Oh, okay.
Yeah. So today I'm going to teach you about something called the Tutte polynomial. I'm going to spend maybe this week on this topic. And let me just start by reminding you a bunch of things that we've seen so far. There's a lot of equations that we've seen that look the same. For example, for the number of regions of an arrangement. The regions of the arrangement equals the regions of the deletion plus the regions of the contraction. The bounded regions satisfy the same recurrence. Then we saw that the characteristic polynomial satisfies basically and we said actually that this is true if H is not a loop or a coloop. The same thing happened here. For the characteristic polynomial, we saw the same thing happened, except with the minus sign. And there's other places where this happens, which I haven't mentioned yet. Make sure this is on. Yeah. So, for example, look at the basis of a matroid. What are the bases of the deletion? These are the bases that the basis of M with E deleted are the bases of this guy that don't contain E. And the bases of the contraction are the bases that do contain E. Then you delete E from them. In other words, you can separate the bases of M into the ones containing E and the ones not containing E. And so therefore, the number of bases of a matroid satisfies the same recursion. You should, and this requires a little bit of a proof, but it's true and you can figure it out. And you can also convince yourselves that the same thing is true for the number of independent sets of a matroid. And what we're going to see is that this keeps happening a lot. These are these things that we call deletion-contraction recursions. We've seen that there's many of them. And when you start seeing something happening so often, you start wondering, is this a coincidence or are these just special cases of some more structural thing that's going on? The question is, are these special cases of some more general phenomenon. And my plan is to convince you today that they are. Okay. So basically what we're going to do is study functions that behave like this, that satisfy a deletion-contraction recursion. And these things are called Tutte-Grothendieck invariants. A Tutte-Grothendieck invariant is a function f that assigns to each matroid some element of a ring. Let's say it's a commutative ring.
Assigns an element of the ring, though, not the ring.
So it's a function from the class of matroids to the commutative ring, to a fixed commutative ring.
So you're okay. So you're not assigning a ring to the matroid. You're assigning a ring.
So maybe I should just say, yeah, this is confusing because this is plural, but this is singular.
Yeah.
But maybe I should just say R, where R is a commutative ring. Satisfying some properties. And the first property is a very important one, and it's the reason that you call this an invariant, which is that if you have the same matroid, then you should be assigning the same element to it. But the same meaning isomorphic. So if you have two matroids that maybe have different presentations, but really they are isomorphic, then you should be assigning them the same thing. Okay. Now, when I say this, of course, you should be thinking of these functions. So, the only reason I say commutative ring and I make it at this level of abstraction is because I might want to assign numbers, like number of regions or number of bases, but I might want to assign polynomials, like the characteristic polynomial. So all I'm saying is I'm assigning something to a matroid, and this might be a number, it might be a polynomial, and usually it's either a number or a polynomial that we care about. So to the same matroid, you assign the same element of the ring. And the second property is this deletion-contraction recursion. The function at the matroid should be the sum of the function at the deletion and the function at the contraction, if E is not a loop or a co-loop. Okay. So it should have this deletion-contraction property, and then so this tells you how to take a matroid and delete elements that are not loops or co-loops. And now I need to tell you how to delete loops and co-loops. Now the point is that a single loop is a matroid. I mean, there is a matroid consisting of a single loop. And so f of loop is a well-defined thing. And f of any loop is the same thing. And the same thing, f of a co-loop is a well-defined notion. And so if you want to delete a loop or a co-loop, then what you do is, remember we mentioned that if you delete a loop or a co-loop, then these guys are actually equal to each other, the deletion and the contraction. And so what you're going to do is you're just going to multiply by f of E. Okay, so this is either f of loop or f of co-loop. If a function satisfies these properties, then it's called a Tutte-Grothendieck invariant. Okay. So, for example, yeah, for example, the bottom two over there, number of bases and number of independent sets, are Tutte-Grothendieck invariants. You have to check that they satisfy the second property as well, but they do. Okay. The third property, rather. Now, you might want to allow yourself, for example, a minus sign here, so that what we do here also includes the characteristic polynomial. And so a generalized Tutte-Grothendieck invariant is a function such that the first thing is true, the second thing is almost true, but you're just going to allow yourself to put some constants here. So you just allow yourself to put some constants here, where A and B are constants in the ring. And then the third property should be the same. So generalized just means you can put constants in the front. Okay? And the reason why I make this abstract definition is because we're going to see that a lot of things that we care about are generalized Tutte-Grothendieck invariants. So that's the point. The point is that many things we care about are Tutte-Grothendieck, maybe generalized Tutte-Grothendieck invariants. Okay. And we care for two different reasons. Sometimes you care because you just want to count something. So for example, maybe you have a matroid and you want to count the number of bases. Okay? That's a pretty natural question. And if you want to answer that question, well, as I said, the number of bases is one of these functions. And so if you are able to develop a theory of these functions, you will be able to count bases, or count independent sets, or compute characteristic polynomials, or compute regions of the arrangement, etc. The other reason that people care about this is to be able to tell two matrices apart. So if I give you two matrices, how can you know if they're the same one or not? Well, if they are the same, what you have to do is find an isomorphism. Maybe you can do that. If they're not the same, how do you show that? How do you show that two matrices are not the same? It's not so easy, but this helps, different invariants. And so what you might try first is to say, well, they have a different number of elements. If they have a different number of elements, then they're different matrices. Or you might say they have a different rank. Or you might say they have a different number of bases. These are the kinds of invariants that you care about. And it just turns out that a lot of the invariants that we care about fall into this category. Okay? And so this is why we study them. Now, one thing that you should notice is that, so this is one thing. Another thing that I want you to notice is that if you have a Tutte-Grothendieck invariant, then as soon as you define f of a loop and f of a coloop, you have defined it for every matroid. If you define f of loop and f of coloop, you've defined f of any matroid. Why is that? Well, because you start with a matroid, and then you just kind of start deleting and contracting, deleting and contracting, deleting and contracting, and you just keep making smaller and smaller and smaller matroids. And whenever you have a loop, you can drop it. Whenever you have a coloop, you can drop it. And you can keep basically breaking your matroid until you get a matroid of one element that is either a loop or a coloop. And we'll actually do this in an example, but you'll see that as soon as you define f of loop and f of coloop, the whole invariant is defined. Okay? But one thing that you should be worried about is that this might produce different results. So if you start with your matroid and then maybe you delete and contract element 7, and then 6, and then 3, and then 2, and then 4, and then 1, you're going to get some answer. F of the matroid equals something. But you might do it in a different order. First you contract 1, then 2, then 5, and so on. And the question is, why do you get a different answer? Do you get a different answer? Maybe you don't. And so that's another thing we're going to have to figure out is whether this is well-defined or not. Okay. But this is the theorem that tells us everything that's going on. It's a theorem due to Brilowski. And it says that there is a unique function from the set of matroids to the ring of polynomials in x and y with integer coefficients. In other words, for each matroid, you want a polynomial in 2 variables. And this polynomial should satisfy 1, that if m and n are equal, are isomorphic, then they have the same polynomial. So the polynomial in 2 variables that you assign to m should be equal to the polynomial in 2 variables that you assign to n. The second property is that this should satisfy the deletion-contraction recursion. If E is not a loop or a co-loop. And the third property is that if you want to delete a loop or a co-loop, then you can, but you have to do something different. So you have to do what this tells us to do. First, you compute the invariant at the loop or the co-loop, and you multiply that by the invariant of the deletion. Actually, let me renumber these. So I'm going to call these 3 and 4, where the second one that I skipped is that basically x and y are the polynomials that you assign to the loop and the co-loop. So for the co-loop, the polynomial is x, and for the loop, the polynomial is y. In other words, this guy right here, when you're trying to delete a loop or a co-loop, then what you're multiplying by is either t sub loop or t sub co-loop. So this is just an x or a y. So this is an x for if E is a co-loop, or a y if E is a loop.
So is the hard part of this theorem showing that there actually exists such a function? Because by that condition, you already said over here that once we have it, it must be unique, because we defined it for loop and co-loop.
Right, so I claimed here that as soon as I define f of loop and f of co-loop, I've defined f of any matroid. And here I did define loop, t of the co-loop, t of the loop, and that says that I have defined it t of any matroid. But really the content here is this well defined? I mean, can I do it in one order and a different order? Am I going to get the same answer or not? Okay.
So it's the existence rather than the uniqueness.
So it's the existence, not the uniqueness that's difficult. Okay. So this is what's called the top polynomial. If the top polynomial Okay. And so maybe I'll ask you to leave some space in your notes to write maybe this much. However much space that takes you, I'm going to add something to this theorem. So leave space for that. But before we get too abstract, I want to make this very concrete and show you that you can compute these things. It's pretty fun to compute these things, actually. You're not going to be able to stop yourself once you start. Let's compute the top polynomial of some matroid. I don't know. Well, I do know which one we're going to do. You do too. So we always do the same matroid.
Does that matroid have a name?
No, you guys could call it, I don't know, the asteroid. I don't know. You can come up with your name for the matroid. So the matroid of our favorite graph. Let's see if this writes. Yeah. Oh, but I think on the video the green doesn't show. I'll show you how to compute these guys. So element 1, 2, 3, 4, 5, 6. Okay. So here's the matrix that we want to compute the top polynomial of. So what are you supposed to do? Well, you just kind of recursively chop it up into smaller matrices. And the way you do that, well, we have a lot of choices here. You know, we could delete and contract 1, delete and contract 2, so on up to 6. Now, if it was up to you, what would you want to delete or contract here?
I'd like to use a loop or a co-loop. Yeah.
So yeah, probably if you can, you should use either a loop or a co-loop, because then it doesn't branch. I mean, if I got rid of the element 1, I would have to branch into the deletion and the contraction. But if I get rid of 6, there's no branching to take place here. All you do is say, okay, 6 is a loop, and so whenever I see a loop, I'm supposed to assign, did I say x or y? Y. So I'm going to delete 6. And when I delete 6, I'm supposed to put a factor of y. And then I just delete it. Okay, so okay, what do I do next? Again, I have many choices, but the best thing to do is use the co-loop, because it's not going to cause any branching. So let me delete element 5. Element 5 is a co-loop, and so whenever I have a co-loop, I have an x appearing. And now I have this guy. Okay, now what would you like to delete or contract? Unfortunately, we don't have any loops or co-loops anymore, and so we are going to have to do something serious here. You know what? So I already did it in the notes, and I already got an answer in the notes, and so I'm going to show you that you do get the same answer by getting the same answer that I got in the notes. And I'm going to let you guys pick the order. It's very bold of me. We'll see if this happens. So I don't know, what would you like to do next? Which element? Miranda, pick a number between 1 and 4. 4. I picked 4, so pick a different one.
2.
2? Let's do 2 because 3 and 4 are kind of the same thing, right? So let's do 2. So here's 2, so you either delete 2 or contract 2. If you delete 2, then you're left with this guy. If you contract 2, then what do you get? You get basically these two guys get morphed over here. You get a loop here and two parallel elements like this. Okay. So this is branched. Now, I don't get any extra factors here because my recurrence just says this guy is this one plus this one. Okay, now let's do this one. So, Chris, give me a number between 1, 3, and 4. 3. Okay. So we're going to delete 3 and contract 3. So if you delete 3, you get this graph. And if you contract 3, you get this graph. Okay. Now here, we're left with a matroid that has two loops, right? And so we can do one of them, which it doesn't matter what the order is. We get rid of one of them, and I said coloops are what? X's. So I get rid of one of them, that gives me an X, and it's 1, so I get this guy. And now there's no more branching to do. The top polynomial of a coloop is X. Okay, so there's nothing more to do there. Now let's do this one. So these are the elements 1 and 4, so, well, it doesn't really matter which one we do first, right? Because they're both the same. So let's maybe... Now, neither is a loop or a coloop, so we have to do them. Just delete 1. Delete 1 and contract 1. If you delete 1, then you get this guy. And if you contract 1, then you get this guy. Okay. Now, this is a loop, so the polynomial of a loop is X. This is a coloop, so the polynomial of a coloop is, sorry, the other way around. Coloop is X, loop is Y. Now we go here. What should I do next?
Get rid of the loop.
Well, here I have a loop, so let's get rid of that loop. And what's the number of this loop? It's 1. So I get rid of 1. And because it's a loop, it should give me a Y. And the graph that I get looks like this. And then it doesn't really matter what I do. These are 3 and 4, so either I delete 3 first or I delete 4 first. It doesn't matter. The point is, if I delete, I get this guy. If I contract, I get this guy. This guy gives me an X. This guy gives me a Y. So now I did all my branching off, and then what am I supposed to do now with all this information?
Add and multiply.
So this is somehow supposed to give me a polynomial. Now the question is, what do I add? What do I multiply? Well, for this guy, I get Y times this guy. For this guy, I get X times this guy. So far, I get XY times whatever I get.
Right.
Now here it branches into this guy plus this guy. So I go XY times this guy. This branches. So on this branch, I get XY XX, meaning X cubed Y. On this branch, I get XY X, X squared Y. So basically what I do is I just travel this tree in every direction. X, Y, Y. This gives me an XY squared. Then I come up this way, Y, X, Y, X. So this gives me an X squared, Y squared. And then Y, X, Y, Y. X, Y cubed. So my top polynomial is this guy. It's a pretty amusing way to waste your time. Now hopefully I got the same answer. X cubed Y plus X squared Y squared plus X squared Y plus X Y squared plus X Y cubed. Same answer. So hopefully this convinces you that once you define it for a loop and a coloop, you're done. You've defined it for every matroid. But what is not clear yet is why different branching orders, here the order was 6, 5, 2, 3, 1. But different branching orders could give you different answers. And the question is why not? Why is this well defined? And that's really the main content of this theorem. So, proof of the theorem. From this, it should be clear that that if you define the T of the co-loop to be y and T of the loop to be x, then you've defined T for any matroid. But the question is, did you over-define? Because for each possible tree that you can draw in this way, you get a different definition of the top polynomial. And the question is, do these definitions agree? But did I... Do they over-define? Do they over-define? In other words, does this depend on the order? Of the elements you delete and contract? Of course, the answer is no, because if the answer was yes, then we wouldn't have a theorem here. And the key reason why this is well defined, as we will see, is that you should remember that deletion and contraction commute. That's the key reason. Okay? And the point is this. Just going to give you a sketch of the proof. Let's say that you first get rid of E, and then you get rid of F. Okay, so first you delete E, contract E, and then you take each one of these guys and you delete F, contract F, delete F, contract F. This is what you get if you do first E and then F. Okay. What do you get if you do first F and then E? You delete F, you contract F, and then you delete E, you contract E, you delete E, you contract E. Well, fortunately, deleting E and deleting F is the same thing as deleting F and then deleting E. Contracting E and deleting F is the same thing as deleting F and contracting E. And contracting E and deleting F is the same as deleting F and contracting E. And contracting both of them is the same in either order. Okay? So the leaves did get reordered, but they are the same leaves. And so when you do this branching, you are going to get a different order of the terms, but the terms that you get are the same. They're just juggled around. Okay? Now, to get a complete proof, you would have to make sure that this also works for when loops and co-loops are involved. But you can do that. Okay? And that's really all there is to it. Okay. So that shows that this top polynomial is well defined. It exists. It is a polynomial in two variables. But what's the second part of this theorem? Which is, in a sense, the more important part. Let's say that f is a Tutte-Grothendieck invariant, meaning f is any function that satisfies the deletion-contraction recursion. Well, then, if you want to know what f of m is, then you just have to know what f of a co-loop is. You have to know what f of a loop is, and you just plug in these two values into the top polynomial. So f of any matroid is the top polynomial of f of the co-loop, comma, f of the loop. Which is amazing. It means whenever you want to compute a Tutte-Grothendieck invariant, all you have to do is compute f of the co-loop, f of the loop, and you've computed the invariant. Assuming you know what the top polynomial is. And this shows you the importance of the top polynomial. If you can compute this top polynomial, you can immediately compute any Tutte-Grothendieck invariant. Okay. And actually, you can compute also any generalized Tutte-Grothendieck invariant. So remember, it's generalized if you have an extra constant a and b lying around. Well, these, again, if you know the top polynomial, you know this invariant. All you have to do is, what is it? A appears out here. B appears out here. Times the top polynomial of f of the loop, f of the co-loop divided by a, f of the loop divided by b. Okay. So again, I mean, this is a little bit messy, but it just says if you have any function which is a generalized Tutte-Grothendieck invariant, then all you have to do is plug in f of the co-loop and f of the loop, and you have a formula for your function. Chris? No, because the rank is positive, and at most equal to the size.
Put in the inside.
But they're in the side of the function.
Oh, they're in here.
So A and B have to be units and R.
Yeah, sure. I mean, like I said, usually these are just numbers or polynomials, and so these issues just don't come up. When you have to write a theorem, you have to put whatever hypothesis. But the point is that this is never a problem. Whenever you have an invariant in your hands, you just plug in here and it works. Okay. And so really the point is that somehow the Tutte polynomial it's the mother of all invariants, It's the, if you can find it, you can find anything. Well, of all Tutte-Grothendieck invariants. And there's a formal way to say this, which is that it is the universal Tutte-Grothendieck invariant. Whenever you study a little bit of category theory, you'll see that this is kind of a standard categorical construction, and universal means, in categorical language, it just means this. If you have any Tutte-Grothendieck invariant, then it is a special case of the universal one, basically. And so the answer to the question that I posed at first, is this a coincidence that we have all these things? Well, the point is that they are all special cases of the Tutte polynomial. And so we would like to understand this polynomial, know everything we can about it, because it tells us everything about all these different invariants that we care about. Okay. What's next? Any questions about this stuff? So there's kind of a disparity between that kind of dry definition and then this very colorful way of computing these polynomials, right? And this is one thing that you'll find in the literature. Whenever people define Tutte polynomials, they do it in different ways, and you almost never see this picture, which is how this picture is one of the good ways of computing Tutte polynomials. The way that I defined it is meant to emphasize the importance of why this is such a good invariant to understand. But most people, whenever you see it in the literature, people will say definition. But for me, this is not a definition. This is a theorem. Because I already defined the Tutte polynomial for you. And the theorem is that you can compute the Tutte polynomial in this way. I don't know if you see what's coming. I mean, remember that the characteristic polynomial had a formula that said, if you want the characteristic polynomial, then what you're supposed to do is add up over all the subsets and then something here. Okay? Well, we have a formula like that here, which goes like this. If you want the Tutte polynomial of a matroid, then what you do is compute this thing. Okay. That's the Tutte polynomial. And so, of course, there's an obvious advantage and an obvious disadvantage to saying it this way. I mean, if I start a class saying this is the Tutte polynomial, then you wouldn't know why you should care about this thing. but the advantage is that here it is. I define it as this abstruse object that exists and is well defined. But this is a much more concrete definition. Here it is. If you want it, there's a formula for it. And so it's good to keep both things in mind, that this is the formula and this is a very concrete definition, and that's really the reason to care about it, and the very nice property of it, that is the universal TG invariant, Tutte-Grothendieck invariant. Okay? How do you prove this? Well, you have to check basically that, I mean, we said that theorem showed that there is a unique polynomial that satisfies those properties. And so what you have to do is just check that this guy has those properties, and then it's going to be the unique one, right? The first property was that if you have two isomorphic matroids, they have the same polynomial. Why is that true? Well, the reason is that the Tutte polynomial is defined in terms of the rank function of the matroid. But if two matroids are isomorphic, they have the same rank function. And if they have the same rank function, then no matter how messy this formula is, it's the same for both guys. The second thing you have to check is that if you have a call loop, if you plug in, what you're going to get is that this is a x minus 1, y minus 1 to the 0, plus x minus 1 to the 0, y minus 1 to the 0, which is x minus 1 plus 1. And if you do it for the loop, then when you plug in carefully, make sure you don't make any mistakes, and you're going to get x minus 1 to the 0, y minus 1 to the 0, plus x minus 1 to the 0, y minus 1 to the 1, which is 1, plus y minus 1, which is y. Okay. And the third one is that you satisfy deletion-contraction. But again, I'll remind you that we proved deletion-contraction for the characteristic polynomial. And the way we proved it is that we derived a formula like this, which looked almost exactly the same as this one. So there's this, I called it Whitney's formula. Whitney's formula says the characteristic polynomial of a matroid is given by a summation. And I used that to prove this identity for the characteristic polynomial. If you do the same, it's the same proof. So this is the same proof as for the characteristic polynomial using Whitney's formula. Okay, and the fourth one is the same. I mean, the fourth one says if you delete a loop, if you delete a co-loop, you add an x. If you delete a loop, you multiply by y. This is for a co-loop. This is for a loop. And again, the same proof for the characteristic polynomial works for the type polynomial. So this is some work, but you just check that everything works out. Okay. Okay. I told you that I'm not assigning any more homework, but I'm going to give you guys things to think about that I really want you to think about. And so here's the first one that I want you to think about, talk about it on the forum, whatever. Exercise. What you're going to do is compute the top polynomial of the uniform matroid of 4 elements of rank 2, and you're going to do it in both ways. You're going to, using the tree, you're going to do it recursively from the tree, and directly using the formula. And you're going to do it enough times so that you get the same answer. You should get the same answer. When you're done with that, you're going to see that you'll be able to compute. Well, basically what I'll ask you is this. How can you tell whether a matroid M is uniform if I just give you the polynomial. Okay. I claim that if I give you a top polynomial, then immediately you can tell me the matrix is uniform or it's not uniform. And what I want you to figure out is why that is. So the answer to those will be on the forum when you guys figure them out. And it's a good place to stop.
I go slow.
I get tired like really slow.
I get tired on the first floor.